Yeah. So you did direction of
So the first time wasn't true, the second was true, or something, one of them wasn't true.
That's where it's very.
All right, so let's recall what we have accomplished last time. So we noticed.
Yep.
So first, we will say that a set A has cardinality no bigger than the set B. If what? If there exists a what? Function, precisely. Function from where to where? From A to B. And this function is injective. Okay? That's intuitively clear. You can verify a bunch of other principles, but here, I would say that the set of fingers on my left hand no bigger than the set of fingers on my right hand, because I can place each finger from the left hand exactly onto one finger from the right hand. The map in this case is not onto. But if I just have one function f that is not onto, does not mean that another function is not onto. Make sense? Well, that's what happened with the integers. That's the problem. So a lot of you think, well, the even integers is a smaller set than all the integers. Why? Because what you do is you take the even to even, and you miss the odd. So you created one injective map that is not onto. But there does exist another function that is both one-to-one and onto. And that's why even integers and odd and all the integers have the same size. Okay? You can also, you can see that this is equivalent. You can also say that this is if there exists a function from G, a function G from B to A that is onto. You can see that this is also going to be true. Okay, and then because of that, we have observed that as a consequence of this result, the cardinality of the natural numbers, which is designated with the letter aleph null, is the smallest infinity. And by that, what I mean in terms of this discussion is that there will always f from the natural numbers to A, where A is infinite. A is an infinite set. There exists always that is one-to-one. Okay, so we always have this problem. Another thing we observed is that uncountable infinities exist. So for example, R, uncountable. And that means that the inequality is strictly, the natural numbers, the size of them is strictly smaller than the size of R. And then we observed, I'm going to review this last part, is that there is no biggest infinity. Now let's review the argument for why there is no biggest infinity. So to show there is no biggest infinity is to show that no map from a set A to its power set can ever be onto, right? So that's how you can generate bigger infinities. Just take a power set. No map F from A to its power set is onto. Right, so there is no hope. Obviously, an F that is one-to-one will exist, correct? What do I do? How do I create this map? I just take each element into its package. Right, so I can just take, obviously I would say, F could be one-to-one. Why am I saying obvious? Well, all I can do is I can define F of A to be the package A. Right? That's going to be a subset, a singleton subset. So this is going to be injected. Now, why can't a map be onto? Cantor had a very clever argument. Some people always find issue with it. There might be more difficult, intricate things hiding behind it, behind the argument. So some people never accept it. But this is how the argument goes. For any F, consider S sub F to be the set of X belonging to A in such a way that X is not a member of F of X. So the analogy I try to use is the set of dissatisfaction, right? So truly it happened to me in France all the time at every step, because I never learned French, even though I went to a French-speaking school and they forced it upon me. So what you have is, this is the situation. So think of this example. If you have A, so we have F is going to be some map from the set A, B, C, and those are just three candies into the power set of A, B, C. The power set contains 8 elements in this case, so there is no need to do any complicated argument. But remember, so what this means that X doesn't belong to F of X, why do I call this the set of dissatisfaction, is try defining what happens if I point at those candies. What box am I going to get? So it could be that, let's say, it could be that my F is this. So it could be that I get nothing if I point at the candy A. So I get box containing nothing inside. It could be that when I point at B, if I point at B, I will get B and C. And if I point at C, maybe what I'll get is A and B. So this is just an example. Can you see what is going to be the set of dissatisfaction in this case?
A and C.
So dissatisfaction is you open the box and you don't see the candy that you pointed at. So if I open the box, then I pointed at candy A, I see nothing inside, so I'm very disappointed. So A is one of the candies I pointed at and didn't get satisfied. If I pointed at candy B, well, that's fine, right? You see, this is f of B, right? B belongs to f of B. You all understand this? And on the other hand, does C belong to f of C? No, right? F of C is this set. So the set of dissatisfaction in this case is AC. So the counter argument, notice look at this S sub f. This is a subset of A. It's a subset of the set. And nothing I can point at, this function cannot produce the set. If I point A, if I point B, if I point C, I never get S sub f. Okay? So the idea is to do it in general. That's the general situation. And then to show that I will never get this set. I can never produce it by any element. So if I consider S sub f equal to this thing, then I can ask, is this in range? Is S sub f in range of f? And the answer is, let's give the argument and then we will verify. So if yes, then we can consider that there must be an element. So then there exists some y belonging to A, such that f of y is the set S sub f. In other words, if I point at some candy, I get that set of dissatisfaction. So then we can consider the cases. So y either belongs to this set or it doesn't, right? So you can look at this. If y belongs to f of y, by definition, y doesn't belong to S sub f. Because S sub f only gathers the candies that I don't find in the boxes that I receive when I point at them. Yes? You see that if y is here, then y is not there. So the sets are not, so it cannot be that f of y and S of f are the same sets. They are differing at least on one candy. In one case, y is inside the box. In the other case, y is outside the box. True? If y does not belong to f of y, again by definition, y will have to belong to the set of dissatisfaction. So the conclusion is no such y is possible. In other words, the answer is no. So here is a very useful and important question when you consider sizes of sets. So question. If the size of set A is less than or equal to the size of set B, and the size of set B is less than or equal to the size of the set A, can we conclude that they are the same? Can we conclude that the cardinality of A is equal to the cardinality of B? Okay? This is not a simple question, although you're used to inequalities, right? You think if A is no bigger than B and B is no bigger than A, they must be of the same size, but you have to be extremely careful. In this theory, what is the first statement implying? So what we know is only this. There exists a function f from A to B that is injective, or I'll say one-to-one. Okay, that's one thing we know, and we also know by the other statement that there exists a function g from B to A that's also one-to-one. In order to conclude that the cardinalities are the same, I must prove the existence of a function that's both one-to-one and onto. Right? All I know is there is one function one-to-one, another function one-to-one, but how do I figure out if there is a function that's both one-to-one and onto? And this problem was solved by Bernstein. It's known as Bernstein's theorem, I think. He might have been very young, maybe 21 or even 19, I don't remember. I think his age is written in Karoko's textbook. You can look at it. He was very young and he came up with the proof that I'm going to present. So pay attention, it might be difficult. So, Bernstein's theorem. The Bernstein's theorem says that A less than or equal to size B and B less than or equal to size A implies size of the set A, cardinality of A is the same as the cardinality of B. In other words, there will be a bijective map, but that's not easy to see. So let's try to see. You see, I only have this F and this G that I work with. I know nothing else about those sets. Obviously, the answer has to do with those F and G. I don't know anything about A and B. I cannot construct anything more clever. So here is what can happen. So what I can do is I can look at the set A. And I can look at the set B. So somehow I want to partition A so that on part of A I will act by, so I want to do something like this. I want to take part of A, let's call this S, and on this part will be mapped by F onto this part, which I can label as F of S, the image. Remember this notation? I hope it's not new to you, right? All this means is that every point of S, I apply the function F to it, and the reason it's called image is if you graph it, it looks like a picture. Right? If I have a picture of S, I take every point in S, and I see where it goes. Okay? So F will map in here, and then the problem is that if I look at this set is B throw away F of S. So this is everything that remains outside of. If F of S is the entire set, well, actually, let's not consider those cases. So this, whatever it is, there will be a set F of S, and whatever is in B that remains if you throw out, exclude any element of the image under S. But then you see, then I would have liked this box to match to this box, which is not always going to happen, right? It could be that what will happen is that when I take this box and I take its image by G, I take the image by G, it could be that the box is going to be maybe too big. Let's say too big. So it could be, this would be G of B throw away f of s. It could be that the box will be too big. It could be that the box will be too small. It could actually, not be onto. But what I want to find an S so that the situation is as follows. So that this picture is true. Alright, I want you to pay attention very carefully. Do you understand what I mean? This is schematic, right? So if I just take any subset of A, it's going to be mapped somewhere. I just drew it as a box here, right? Now, what remains, I don't know where it goes. What remains, I want it to neatly go to what remains when I take A and I delete S from it. I want it to be exactly here. Because if not, if this is the situation, then I can define a function. You see, I can say that if I have this neat structure, like as I drew below, I can say that the one-to-one and onto function is going to be defined to be f here and g inverse here. You see, because this and that, it's a one-to-one. So from this lower box to this lower box, there is a bijection, right? So it's always true, right? From this lower box to this orange box, there is a bijection. But if they overlap, I don't have a good definition. Or if something is missing, it's not onto. Right? Not well defined on A if you go from A. Do you understand what I'm saying?
So we're trying to prove that that's equal to A without all of the elements S.
Yes. So we're trying to prove that one such S exists. If you try with functions, it's not easy to actually come up with one. But this procedure will tell you how to come up with that S. So here is what we want. In other words, we want S such that if I take A and I remove S, I get the same thing as G applied to B, remove f of S. You see this? Whatever is left if I delete S will be the image of G. And then there is a neat separation and there is a way to define the map. So now what I do is I can simplify it further. I can make it. I can make this process as a process when you search for a fixed point. What I can do is I take A, throw away this. So you can say that S should then equal to A, throw away G of B, throw away f of S. That's what S should be equal to. Okay. So it will be a fixed point of some function. So here is what I do. I define a function h, and the function h is going to be from the power set of A back into the power set of A. And here's how it's going to be given. So the function is going to do this. H of u, u being a subset of A, h of u will be equal to A, throw away g of B, throw away f of u. Okay, that's going to be the map I'm going to define, and I want to find the fixed point. I want to find something that I want to find S prime. Fixed point. Fixed point S star of H. In other words, what I want to find is something, some H, S star, so that if I apply H to it, I get that S star back. That's equivalent to what's written here. Okay, you follow up to this step, I hope. So then we make the following observation. First observation is that H, or say observation, H is increasing. Let's prove it. So what do I mean by increasing? So it means that if I have U is a subset of V, which is a subset of A. So I want to say that if I apply H to U, it's going to be a subset of H of V. So in that sense, I mean increasing. Okay. So let's calculate what happens if I do H of U, and let's do it step by step. So if I have this situation, then I hope to conclude H of U is smaller than H of V. So what I do is I first apply F. So notice first F of U. It has fewer points, so that's going to be a subset of F of V. Do you all see that? F of U is a subset of F of V because I apply the function F to the points in U, and here I just have more points to apply to, so of course this is going to be a bigger set. Yes? So then if I take, let's say if you see the next step is I am going to take B throw away, see, because this is B throw away then. So if I take B and I throw away F of U, what's the relationship to B throw away F of V? What's the relationship? Which way do we go? Which is smaller? F of V is smaller. Here I throw less, here I throw more, right? So this is going to go this way. I threw more from B. Yes?
What do you mean by throw away?
What I mean is you cut out, right? You cut out F of U. So this means B remove all the points that are the images under F of in the set U. Now the set U is in V, so here I throw all those points, and here V has extra points, so there will be more F of V's here.
Yeah, what are you throwing away? That's what I'm trying to say. You throwing away numbers?
I'm throwing away elements in the set. So whatever A and B are. Okay, so I hope you see what the image is, right? What is the image under F of some set? This means just whatever points are, however the points in A are scattered, they're going to be there's going to be correlating points in B that are scattered somehow. Okay. So yeah, so the function. So in this case, you see this part. Do you see F of U is a subset of F of V? Well, you see that, and you see there are going to be some points scattered. I project them into B. And actually, in this case, it's 1-to-1. Although that will be true regardless. So I project them all into B. And here I project more points into B, including, you see, V contains all the points in U. So the image will contain, this image of V will contain the image of U. Now, what is this? This is whatever is in B that is not not the image of U. That's what this means, right? So it's like I take a picture and so if this is B, if this is B and this is f of U, then you said yourself that f of V is bigger. F of V is bigger, so it's something like this. Okay. So what remains in B are, well, we can look at points that are in B but not part of f of U. It's pretty much this box where you cut out the middle shape, and B throw away f of V is you cut out the orange shape. So you see, you throw out more. That's what I mean by throw out, right? What survives if I throw away f of V is whatever is in B that is not inside the orange curve. Okay, I hope that helps. If not, again, we'll talk. So this is going to be this case. Now what I do is I apply G. G applied to B, throw away the image of U. What's the relationship to G applied to B, throw away image F of B? How does the relationship go? Which way? Sorry? Well, there is G. So this is a subset of that.
Right. Yeah,
No.
that's what I'm saying. No. Okay.
No,
The other way?
the other way. It's this way. It's just like the beginning. It's really, again, this set looks ugly, but it's really like procedure one. This set is presumably bigger, right? So if I apply G to it, I apply it to more points than if I apply G to it. Yes.
Is the cardinality of a set an integer?
No, it could be an integer only if the set is finite. In general, it's not an integer. There is, of course, a huge theory on cardinality. We just only brush through it. We only are saying two things. We're going to say Aleph null is the cardinality of all the integers, or all the natural numbers. And we might, like in the homework, there is like a brief mention of what's the cardinality of R. But in practice, we don't deal with cardinalities that are different from R or the integers. I'm going to show you examples that in pretty much anything that we're going to cover in class, you don't consider higher cardinalities. But you can generate, obviously, bigger sized sets by taking the power set of whatever you have. If you take the power set of R, it will be bigger than R. Power set of the power set will be bigger than that again, right? But we will see that really only two types of infinity are going to be important in this course. The countable one and that of R. Right. Good? So we have this situation, and now finally we need to take A and throw what we have here from A. So 4. If I take A and I remove G, B remove the image of U, and I have A remove G, B the image of V, which way do we go? The opposite, right? Now again, you see, we apply two procedures, throw away and image, right? So now what is this? This is simply H of U. And we are saying H of U is then a subset of H of V. So we have shown that this function is increasing in that sense. It's mapping bigger sets. So if you take a small set and a big set, the image under H of the big set is bigger than the image of the small set. Okay, so how is that going to help? Well, so what we're going to do is we're going to consider a collection of all subsets. So we're going to consider O is going to be the collection of sets S that are subsets of A, such that S is a subset of H of S. Okay? In other words, you see I take S, I take the image of that S under H, and maybe S is a subset, maybe it's not. I'm going to consider the collection where it could be empty, it could be that nothing works, right? But I'm going to consider all sets that if you just apply H to them, you will see that S is neatly inside. Do you see the picture? So H is really taking elements in A and back to themselves, right? So the picture that you can think of is if this is A, and let's say this is S. I didn't draw it like I did it here. This is S. Oh, actually, let me do it schematically. Maybe it's easier for you, I don't know. So suppose that what I'm talking about is, suppose this is A and this is S. So what I'm looking for is sets S, so that if I apply H to it, I get something that contains S. So maybe that would be H of S. Make sense? So H of S is going to just contain S and maybe more things. So now we are going to take S star to be the union of all of them. So S star is going to be the union over all the S, where S is an element of O. So I take the union over all of them, all such sets. I take their union. I'm going to erase this. You have it. So what happens if is this set itself a membering O? Let's see what happens if I apply H to it, right? So if I apply H to a star, if I apply H to a star, that means that I apply, so let's look at it. So this will be containing a star. Do you see it? Why is it containing a star? Let's look at it this way. So this is a union, right? So I can use the increasing property of H, and I can say this way. I can look at any S compared. So I can look at any S that belongs to a star. Any S that belongs to a star. A star is the union. By the property that we have there, we see that H of S, by the increasing property of H, is going to be a subset of H S star. One second, let me think. Let's do it this way. So I apply so we have S star is equal to this union. Now each S is part of O, so so I know that this is a subset of the union of H of S, where S, damn it. I mean, I think we stay and be burnt here, right? If that's what's necessary.
Do we stay or?
I mean, I think what I like the German expression, right? It's wenn einer von uns fallen soll, der andere steht für zwei, which means if one of us should fall, the other stands for two. You know, that's a very good motto for mathematicians. Sorry, it was me. I started the whole thing. You started it? Yeah.
What do you think I left?
Oh.
They're evacuating, I think.
They are?
I think so.
So we have to.
Well, if they don't find us here, they won't evacuate. So
But they make an announcement on if there's an issue, they have a loudspeaker.
yeah, they're gonna.
I mean, the loudspeaker, they have a loudspeaker that can be heard in all the platforms.
Okay, we'll see.
So if there's a real emergency.
They're having drills. Why is it the best way not to get tested? It's going to be a
Yeah, they're
taking two
well, we can still see the words, even if we can't hear you.
Finally, thank God. Let's shut up. All right. All right. Do you see? There you go. It will be too late when there will be a reason, so therefore stay. All right. So do you see this reasoning? So S star is the union of all of those things. Now, if I were to apply H to all the S's, I just make the union bigger. Do you see that? Because by this hypothesis, right? Each S belongs to its image under H. So this is bigger. And now I'm a bit afraid. Do you see that this union, right? This union means apply H to all the points in S for all the S in here, which means that's the same exact thing as applying H to all the things in O. Yes? Do you see that this and that are the same? Again, think about what you do when you apply this operation. Image. What you do is you take H and methodically you map each point in S somewhere, right? So here, what happens is that you're going to, again, it's the same as taking H and applying to the full union. Since, again, I will have to apply it to one S, to another S. So this part is now H of S star. I hope you see this might be the only thing that you need to think a tiny bit about. So this is S star. So what does it mean? It means that S star is itself part of the union. So then the implication is S star is part of the union. It's an element in O. And now what does it help us? So now I can see what happens if I apply H to S star. Look at it. So that means that H applied to S star, it is a subset of so apply this. So this is going to be a subset of H applied to H of S star. You see, because what did we conclude? We concluded that S star is a subset of H star, and H is increasing, so if I apply H again, I have this situation. So now what do I know? I know that this implication is that H of S star is also part of the set O. So therefore it's part of the union. Okay? S star is contained in H S star, and this H S star is one of the things that we're already taking the union of, and the consequence is we have found our fixed point. The consequence is that we must have, since we have, I'll write it a bit, so since S star is a subset of H S star, and H S star is a subset of S star, they must be equal. So we must have that H of S star equals to S star, and the proof is done. Because that implies that we can partition A into, that implies again what this means is that we can take A and break it into one part. This part will be S star, and this part will be A throw away S star, and this is B. So the image of S star will go in here, that will be F S star, and then the image from here. So this is F and this is G inverse. It will be B throw away F S star. So the function defined by this picture, defined to be F on S star and to be G inverse on A throw away S star, is our bijective map. Okay, so this gives us a lot of very simple ways of showing that sets have the same cardinality. Let's try to see how that might help. Okay. Let's begin with a simple example. So, example, show that the interval 0, 1 is equivalent, it has the same cardinality as the interval 0, 1 squared. So in other words, what I want you to see is that this small interval is the same as the open box. Even though this open box contains many copies, in fact uncountably many copies. You can see I can use the vertical y-axis to see that there are going to be uncountably many copies of this real number line, yet they are going to be the same size. Here is y. So again we need to, this is 0, 1, this is 0, 1. So solution, all we need to do is exhibit an injective map from one set to another and an injective map in the other direction. So first let's take a function f from, let's call this set, okay, so from 0, 1 we can define it simply by identity. So the function is just going to be f of x equal to x. So this is 1 to 1, not onto. Okay? So the conclusion is, if I call this, so the conclusion is that the size of 0, 1 is less than or equal to the size of 0, 1 squared of the Cartesian product of the square. That was obvious. Now, the less obvious is how do I find an injective map from the set 0, 1 squared to 0, 1. Okay, how do I do this? Well, so this function contains two variables. So this would be g of x, y. Right? Any point in here is going to be x and y. Yes? So g of x, y, what I can do is I can represent each of the elements x and y, since they are inside of the interval. I have a representation that is infinite expansion in decimal system, and it's unique. So I can write g of 0.x1, x2, x3, so on. By that I mean the infinite representation of x using base 10, let's say. And here I have 0.y1, y2, y3, and on. Okay? So let's call this non-terminating expansion, right? The one that follows, you never see zeros eventually. Also not terminating. Okay? And now, any ideas? How can I produce out of those two numbers? How can I produce a number in 0, 1 injectively? Well, it would be 0 point. What I can do is I can braid them. I can say 0.x1, y1, x2, y2, x3, y3, and so on. Okay? Because this is going to be an infinite non-terminating expansion, it's unique, so I can always unbraid. I know how to unbraid, I know how to take the inverse if I get one, right? And all I just have to do is the odd ones, they go to the first input, the even ones go to the second input, but this map is not onto. If you think about it carefully, it is not onto. So G is 1 to 1, but not onto. Just like this one is not onto, this one is actually still not onto. One reason for that, you can just think about it. You can construct numbers that cannot be so produced. For example, in 0, 1, there is the sequence. So for example, why is it not onto? So I can take the value z, which is equal to say 0.01010101, etc. Right? So this is non-terminating. You never see zeros. It's non-terminating, but I cannot produce. You see, if I try to untangle it, if I try to take G inverse of z will produce something like 0.0000. Right? That's the first number, and the other number is 0.111, etc. But this is not, this is 0, we don't have 0, we don't have the quarter. The interval does not contain the quarter. So, quarter. Right, this number will lie, this G inverse, it will lie somewhere along this line, which is not really part of the set. So it's not on. But no problem, right? 1 to 1, 1 to 1, Bernstein. So what I'm saying then is that we know that 0, 1, the Cartesian product is less than or equal to the interval 0, 1. And therefore, by result 1 and 2, and Bernstein, those sets have the same cardinality. And by the way, this cardinality is all real numbers, right? It's the same as the cardinality of R. Remember the map that takes 0, 1 to R, right? And recall that the cardinality of R is the same as the cardinality of the interval 0, 1. There is a function that easily exhibits many functions that will be one-to-one and onto. Okay. Now this example is a little. So let's see. So what happens if I take the cube? One direction is obvious. What would be the other direction? What do we do? Yes.
X1, Y1, Z1.
Exactly. We braid with 3, right? So you now see easily that if I take this 2 and I make it even a million, right? Million-dimensional cube has the same number of points as just the line, even though you have uncountably many uncountable copies, right? Well, let's try to do something worse. Let's see if we have infinite dimensional, right? So not just finite dimensional, let's go right away to infinite dimensional. So the notation in the book, again, it can be a little misleading. So some use omega, right? So some books, they're avoiding the symbol infinity that you learn from calculus, because again, the symbol is supposed to mean growth without bound. So here's the example. So some books would say something like this, 0, 1 to the omega. I will write it still, forgive me for that, or I'm using notation, I'll write it like this. Okay, and by that all I mean is countable Cartesian product. It's just 0, 1 cross 0, 1 cross 0, 1 cross, etc. So this is 1, 2, 3. So that would mean infinitely countable Cartesian product. Make sense? So this again is abuse of notation, because this I said is supposed to mean growth without bound, but now I made it mean something else. I made it mean this. This is well defined. How do we go about, and well, what do you think? I mean, I actually maybe answered this question, but do you think it's bigger or not? We see that all cubes, hypercubes dimension 5, 7, 27 billion, all are the same as the size of one interval. What if I have this infinite dimensional cube? Will that be any different? How do you show that it's not? So in this example, I'm claiming that 0, 1 is equivalent in size to 0, 1 infinity. And therefore, the real numbers have the same cardinality as the infinite dimensional space generated by real numbers. You can show that directly. So one direction is obvious. So I take f from 0, 1 to 0, 1 infinity, and that will be just defined by f of x equal to x 0, 0, 0. So that's called embedding, right? I just take x and I just make it one of the axes. Clearly this is injective. So that part is easy. The second part is how do you figure out what to do in the second part. So second part, let's consider a function g from 0, 1 infinity many Cartesian products to 0, 1, and let's try to do it this way. Let's say that, so first of all, we have g of x1, x2, x3, x4. It is a sequence, infinite sequence, okay? And I need to somehow make sure that I braid them, all of them. You see, 1, 2, 3, I might miss some of them. I have to braid some of them in a very good way. So I can then first expand those numbers in base 10, let's say. So that would be g 0.x11, x12, x13, and onwards. So the one on top indicates not power, but indicates just which x, right? So this means they are all part of the first input. This is an ending decimal expansion. The next number is 0.x21, x22, x23, etc., and etc. You get the idea, right? So each of them has a unique unending expansion in base 10. So then what I do is I'm going to now define, I'm going to say this is going to be y, which is going to be equal to 0, y1, y2, y3, etc. And then I'm going to say what's y sub n. Y sub n is going to be the following thing. So it's going to be 0 if n is not prime to some, is not a prime to some power k. So in other words, if yn, so this is prime. So each integer has a unique expansion by primes. Okay. So if I see that the number is not a prime to some power k, I right away set it 0. So for example, what goes to 0? Let's say if you take the number 1, right? So the first number, y1, right? y1 will be 0, do you agree? Because 1 is not a prime to some power of k. What about 2? 2 is 2 to the power of 1, it's a prime to the power 1. 3 is a prime to the power 1. 4 is a prime to the power 2. 5 is a prime to the power 1. 6 is 0. 6 is product of two distinct primes. It's not prime to one power. Do you see what I'm saying? So first of all, this thing is going to annihilate everything that's not a prime to some power, okay? And then what it's going to do is it's going to be it's going to write x. It's going to braid x. Let's see. So x j x, let's say x, we'll write it like this, x j sub k, if n is the jth prime to the power of k. Okay, that's how I define it. So how does this function work? Well, let's just give an example. So suppose we have g of 0, 0.1, 1 to blah blah blah, 0.3, 394, blah blah blah, maybe 0.0, let's not use, say 5 to 1, 3, blah blah blah. Okay, so the numbers that I'm going to look here, look at it. So you see the first number here, the first prime is 2. So this corresponds to 2 to the power of 1. This corresponds to, so this guy, I will map it at 2 to the power of 1. This guy, because it's the first prime, will be 2 to the power of 2. This guy is going to be in 2 to the power of 3 position. Okay? Where am I going to find those numbers, 3, 9, and 4? Where? Well, I'm going to look at this guy. It's going to be 3 to the power 1, 3 to the power 2, 3 cubed. Okay? So the second number corresponds to the second prime, which is in 3s. And the next will be the third prime, that's in 5s. Yep, so that would be 5 to the 1, 5 to the 2, 5 to the 3, etc. So then what is G going to do? So G of such numbers is going to be equal to, so first it will be 0. First position is 0 always, because this corresponds to 1. Next position, this is second position. Second position I look to 2 to the power of 1, so this would be 1. Now this is third position. What number goes in?
0.
No? First position, second position, third position. What goes in? 3. You see, because again, what I'm saying is, what you look here is, you see that this number, you see this index is 1, this index is 2 to the power 1. So 2 to the power of 1 means first prime, so that means I look into the first number, and the 1 means it tells me how to look through the digits, okay? So that's 2 to the power of 1, and this is 3 to the power of 1, so this means I look to the second number and I take the first. The next, what's the next number? The next number is 4, 2 to the power of 2, so what goes here? 1 again, right? It's 2 to the power squared, it's this one, okay? So it's 1. And then what's the next? The next is, so this is now 5, so 4, 5, what goes here? 5 actually, because this 5 starts with 5, so it's 5. What goes after 5? 0. So 6 is 0, and then I haven't displayed 7, so I don't know, right? 7 would be the next thing, right? I only wrote 2, right? So then next I don't know. Make sense? Now, do you see that this function is injective? Because why do I know it's injective? I can unbraid it. I can figure out by looking at those numbers. I can just quickly, I can start sorting them, which goes where. So G is injective. 1 to 1. But obviously not onto. Do you see? For example, I never have anything other than 0 in any indices that are not powers of primes. It's 1 to 1, but not onto. You see? It's a bit hard to display a 1 to 1 and onto map, but by Bernstein I don't need anymore. You see? I displayed 1-to-1 from one direction and 1-to-1 from the other direction. And if you understand Bernstein, that means that one function like this will exist, even though I'm not sure what it might look like. So yeah, so the conclusion is as desired, is that indeed the cardinality of 0, 1 is the same as the cardinality of 0, 1, even of an infinite dimensional space. All right?
So to get to a higher cardinality, we can take the power set.
If you take the power set, it's one way to get to higher cardinality. There are other ways, of course, right? There are things that, let's say I took a countable Cartesian product. Maybe you can take an uncountable Cartesian product and define what that would mean. Will that be the same cardinality? See?
So if we take the power set of the natural numbers, we get a higher cardinality than the natural
Yes,
numbers.
if you take the power set of the natural numbers, you get a higher cardinality than the natural numbers.
Now, how do we compare that? What if we want to compare that
Oh,
cardinality
that's a difficult
to
question.
the cardinality of the real numbers?
That's a more difficult question, right? You might ask, if I take the power set of the natural numbers, do I get something bigger or the same size as the real numbers? You can think
Or
about
smaller?
it. No, it cannot be smaller.
It cannot be smaller.
I can
It
know.
could be bigger or the same size.
If you think about why it cannot be smaller, if you think about it, again, it's a priori not clear. Maybe it could be bigger, smaller, but I look at it, I know it's either bigger or the same size. Right? Right, guys. Thank you for coming. Have a good one. We begin with metric spaces next class.